Slingshot by Andrew D'Amato, Mike Barthme, and Ben Gardner. So for those who don't understand the ride, it's pretty simple. You sit in that little capsule, which is connected to 4 cables, and the cables are attached to springs at the base or on the ground, and it launches you in the air.
Hello everyone, I'm Andrew D'Amato, and I'm explaining the kinematics part of our slingshot presentation. First, we got to start with our observation question, which is how can we use kinematics to describe the motion of the carriage on the ride? Pretty much we're just trying to use kinematics to further understand how the cart's going to move and if we can predict its motion at all. First, we got to start with some assumptions. The acceleration of the cart is not uniform throughout. The system will be accelerating from the ground or launch point until it becomes even with the 2 metal rods, which is like the midpoint in between the 2 metal rods. The carriage will begin to accelerate in the opposite direction after this point due to the tension forces of the cables now pulling it downward, which I showed in the diagram here with the 2 arrows on the different parts of the ride there. Also, we gotta assume that the cables follow Hooke's law. The cables are already stretched at the starting point. No air resistance, which there obviously is air resistance, but for the math and the numbers, we're going to try to keep them all good by using no air resistance. Also, there'd be no frictions between cables and carriage. Using the equation distance equals velocity times time plus 1/2 acceleration times time squared, we can find the acceleration during each period of the ride. All we have to do is find the time it takes for the carriage to go from one point to the other, and we can find the overall acceleration. We can assume that the position versus time graph created will resemble the one to the right. This is because the force exerted by the cables on the carriage creates upwards and downwards acceleration. The point where the position starts to decrease is the max height of the carriage. The graph is only for the first oscillation of the carriage and does not factor in the remainder of the ride. Obviously, this is only the first oscillation, and it does not return to the initial starting point because at the initial starting point, the cables are stretched significantly, which is why the ride goes up so fast. Now on to the quantitative part. First, we have to start with some numbers here. The carriage starts at ground level, so the initial height is 0. The max height of the ride reaches is 67 meters. The midpoint between the 2 metal poles is 44.8 meters. From slowing down the video, we can see that the carriage takes about 1.68 seconds to reach the midpoint in between the 2 metal poles from the starting point of the ride. Now we're going to do some math, and we're going to use the equation that I talked about earlier. And also, but we got to do sum our numbers first, which the initial height is 0, and initial velocity is also 0 because the carriage starts from rest. So that leaves us with distance equals 1/2 acceleration times time squared. Now it's just some equation manipulation. We get acceleration equals 2 times distance divided by time squared. And we're just going to plug in some numbers. And we get 31.75 meters per second squared. And now for the top part of the ride, from slowing down the video, we can see that the carriage takes about 1.23 seconds from the car to go from the max height of 67 meters to the midpoint between the 2 poles, which is 44.8 meters. The only difference in this equation is we're going to have initial height, which is 67 meters. And then from there, though, it's pretty much the same thing, the equation manipulation. Then we're going to sum in some numbers, and we get the acceleration equals negative 29.35 meters per second squared. Now onto the second part of our quantitative. What this data shows is the magnitude of the accelerations are close but not the same. This means that the carriage's motion is harmonic. This is because the magnitude of the acceleration slightly decreased but remained very close. We can assume that every following oscillation would have a smaller magnitude of the acceleration than the last. Now on potential human errors that could have skewed the data. The video that I analyzed was not filmed on a slow motion camera, making it more difficult to determine the exact time in which the carriage reached various points. We just used the feature where YouTube lets you slow down the video significantly, and that's how I determined my data. The distance have been converted from imperial to metric, causing them to lose a few decimal places in the conversion process. We had to round some of the data because going from imperial to metric is not a perfect system, so we had to round a few numbers. The ride may not run the exact same way every time due to wind, weight of passengers, or freshness of the cables. That could end up skewing the data.
For energy, our observation question is how can we use the work energy theorem to determine the properties of the cable? Our system is isolated, and it's the earth cable passenger carriage system. And then in our system, we will observe the energy at 3 different states. on the ground where h equals 0, at the top where h equals 67, and after crossing the two metal towers at around h equals 45 meters, which you can see on the right. The assumptions we're going to be taking into account are that the cable and the springs in the mechanism follow Hooke's law, that there is no air resistance applying negative work on the system, and that the cable's initial unstretched state lies taut at around 45 meters. This is going to help us determine the elastic potential energy later on. And then also we're assuming that the carriage does not rotate, or that rotational kinetic energy is very little. The system is isolated, so no work is done on the system, and the total energy remains conserved. Initially, as you can see in the graph, all of the energy is elastic potential energy, and as the force of the cable on the carriage pushes the riders upwards, the energy is transferred into kinetic energy and gravitational potential energy. Shortly after passing the 45-meter mark, the sum of forces begin to increase in the negative direction, and the rider slows to a stop, where there's no more kinetic energy because for that instance the system is motionless, or the riders are motionless, and then all of the energy is stored in gravitational and elastic potential energy. And then for the quantitative side, we know that the mass we estimated was around 700 kilos, 75 for each rider, and then we estimated the carriage was weighed around 550 kilograms. And our change of height, which is our initial change of height between 0 and 45 meters is 44.8. And then our second change of height is between 44.8 meters and 67 meters at the top. And our unknown, which we're going to solve for, is the spring constant. And then we use the work energy theorem, which states that the sum of energy in the initial plus work equals the sum of energy in the final state. And as we saw from our bar chart earlier, the initial state is only elastic potential energy, and the final state is also a little bit of elastic potential energy, but mostly gravitational potential energy. And then we use the equations for each energy, and then we solve for k, and we found that k equals 2 mgh divided by the change of hi squared minus the change of hf squared. And then we plugged in our knowns, and we found that k equals 607.1 newton meters. And we can check if this makes sense by plugging it back in. And our experimental acceleration was 31.75 meters per second. And we can use Newton's second law, sum of forces equals ma, where the sum of forces is the force of the cable upward and gravity downward. And then we can solve for a, and a equals m over kx minus mg. We plug in our knowns and our newfound k, and we found that the theoretical acceleration should be 28.57, which gives us a percent error of around 10%, which is pretty good for the assumptions we took earlier.
Okay, although Ben and Andrew both used forces to solve for their quantities, another interesting thing about this ride is how the two pillars are placed. As you can see in the photo, the white lines represent a perfectly vertical tower, whereas on the right and the left of it, the towers are not perfectly straight. This is done so that the horizontal component of the cables can be transferred more effectively to the ground. Our question will be finding the quantity of that force, and some of the assumptions that we have to make so that we can find that is that the towers in the cable are initially at equilibrium. The springs exert a total of 355 kilonewtons on the cart, which is a number that we found on the internet, so it has to be true, but it's a number that we were going to use. And the final assumption that we made was that the cable earth tower system was isolated, which is not listed on the slide. So the reasoning behind our math is that if we can find the horizontal component of the cables, then it should be in equilibrium with the horizontal component of the towers, so that they don't sway drastically while the riders are on the ride. We're using the force of the cable to solve for the horizontal component because it's a number that we could find online. Online, we found that the total force of the springs is equal to 355 kilonewtons. Therefore, each side, the right and the left, exert 177.5 kilonewtons, which I'll go into greater detail in the next slide. I also took a triangle, or I copied a triangle, and put it on next to a protractor to find the angle of the force, which is 20 degrees. So solving for the horizontal component is just basic trigonometry. We found the angle, which was 20 degrees. We found the force that each side exerts on the cart, which is 177.5 kilonewtons. And using the sine of 20, we found the force of the cable, which is 60.71 kilonewtons. This is a pretty significant amount, considering how large the towers are, and if the towers can cancel out that number, it makes the ride safer and more enjoyable for the rider, as they don't have to deal with a constantly swaying tower. Okay, thank you for watching our presentation, and be safe. Enjoy Six Flags.